In this video, I want to talk about inverse trig integrals. These are integrals that will result basically in inverse trig functions. So we know that the opposite of integration is differentiation. So let's start with what we know about the derivative of inverse trig functions. Actually, even before I begin that, I have a video lecture on how to find the derivative of inverse trig functions, as well as another video lecture just reviewing what inverse trig functions are, and reviewing how we restrict the domains. We can have an inverse trig function. So if that's something that you need to review, you can go back and look at those video lectures. I'm not going to do that here. I'm going to quickly review the basic derivatives of three of the inverse trig functions, and then relate that to how do we find integrals that look basically like this. So if you recall, the derivative of arc sine is 1 over the square root of 1 minus x squared. So I'll take these basically one at a time. So going the other direction then, if I had something that looked like this, right? So I have the du is in the numerator, but we could write this as 1 over and put the du out here. But notice the basic structure is the same. We have a square root. A is just a number. So in this case it's 1, because 1 squared is 1. And u is a function, some function of x. So if we let u equal x, then this is exactly the same, right? So if a equals 1 and u equals x, then we end up with this. And notice then if u equals x and a equals 1, then I just end up with arc sine of x. All right, now we just always have this plus c on the constant of integration, because any if I had added any constant to this and taken the derivative, that constant would disappear and I just end up with this. So we need to add that back on. So that's the general idea. We're looking for things of this form, where I have a square root in the denominator and a number minus some function squared would yield arc sine of the function divided by the number. So likewise, for arctan, derivative of arctan is 1 over 1 plus x squared. If I have something of the form a squared plus u squared, then that integral will be 1 over a arctan of u over a plus some constant of integration. Again, if we let a equal 1 and u equal x, we end up with exactly this. So again, notice the difference in the structure here. It's plus, and there's no square root. So if we end up with basically a number plus a function, something that's squared, it's going to be arctan. And then finally, arcsecant, we have, notice how this differs from arc sine. In this case, it's x squared minus 1 under the square root instead of 1 minus x squared, and there's this extra factor of x out front. So when we're looking at the integral, we have this, some function of x out front, and then the function squared minus a number squared. That's going to give us 1 over a, arcsecant of absolute value of u over a. Notice here that the absolute value was in the derivative. Here it's in the integral. It's in the antiderivative. Okay, so that's just to kind of give you an overview. And this is what we're focused on over here. We're going to be looking at integrals of this form, and I think the trick here is to see this form so that you can recognize that it's one of these three inverse trig functions. This was just basically by way of review, assuming that we've had Calc 1 and we've seen the derivative of inverse trig functions. Even if you didn't maybe remember it, hopefully this serves as enough of a review that you can see that going the other direction, taking the antiderivative of something of this form, will bring us back to arcsine or arctan or arcsecant. Okay, so let's look at a few examples, because I think that will go a long way towards helping to understand. I mean, this is kind of alphabet soup up here, just lots and lots of letters. Let's look at a specific example. So, example 1, let's look at the integral of dx over the square root of 1 minus 4x squared. So the first thing is to look at these three and say, well, what form does this seem to fit? Right? I have a square root, and I have 1 minus 4x squared. The only thing that really fits that is this, right? We have a number minus a function squared. All right. So the next thing is let's figure out what a and u are. So a would have to be 1, because 1 squared is 1, and u I'm looking for something squared that would give me 4x squared, right? So clearly that's going to be 2x, because 2x, if I square that, square the 2, you get the 4, square the x, you get the x squared. And now I need a du, right? So this is basically our substitution, right? This is kind of, it's like the substitution method in the sense that u equals some function. So du is 2 dx, and I have a dx to replace here, so 1/2 du equals dx. So now let's rewrite this in terms of what we have here. So I'm going to bring this 1/2 out front, and I'm going to have du over the square root of 1 minus u squared. Notice now that this perfectly fits this with a equal to 1. So answer, the 1/2 stays out front. That's going to be arc sine of u over a. Well, u is 2x, a is 1, so arc sine of 2x plus c. All right, so that's our first kind of basic example. Let's look at something that maybe is a little bit more complex. Second example, let's look at something like 1 over the square root of 4 plus x minus 3 squared. All right, so again, we're going to look at these three and see if we can determine which of these has the similar structure to this one. So take a moment, see if you can figure out which one of these fits this structure. All right, well, hopefully you see, well, there's no square root here, and this one is the only one without a square root. And I've got something squared plus something squared. Well, I can think of this as 2 squared, and this is x minus 3 squared. So let's let a equal 2, and u equals x minus 3. So du is just going to be dx. All right, so now we rewrite it. It's going to be the integral of 1 over basically 2 squared plus u squared du. All right, and then that's going to give us, if we look here, we said a is equal to 2, so I'll have a factor of 1/2 out front, and then arctan of u, which is x minus 3, over 2, which is a, plus c. All right, so again, these first two examples show that what we want to do is look for a structure in the integrand that's similar to one of these three. All right, let's look at another example. All right, let's look at something like, I've got x squared plus 3 over x times the square root of x squared minus 4. All right, this one's a little bit trickier, but let's just focus on, because of the numerator, but let's focus on the denominator right now. If we look at the denominator, clearly this one fits this, right? I've got this x out front, I have x squared minus 4, which we could think of as 2 squared. The question is what to do with this x squared plus 3 in the numerator. So what I'm going to do is basically break this into two integrals. I'm going to rewrite it as x squared over x square root of x squared minus 4 dx plus the integral of 3 over x square root of x squared minus 4 dx. And we'll deal with each of these separately. So let's take a look at this first one. The first one, I want to point out, I've got a factor of x here and an x squared here. So I can cancel this with one of those, and now that integral becomes x over the square root of x squared minus 4 dx. And let's go ahead and finish this one before we take a look at that one. Notice here that the derivative of what's underneath the radical here is 2x, which is just a factor of 2 off from that. So we can use substitution here. If we let u equal x squared minus 4, du equals 2x dx, I have a factor of x dx to replace, so I divide out the 2. So x dx is replaced by 1/2 du, and this whole thing here is replaced by u. So this is going to be equal to 1/2 integral of du over the square root of u. Alright, which we can rewrite as 1/2 integral. I'm just going to rewrite that as u to the negative 1/2 du, which, after I add 1 and divide, so add 1, that gives me 1/2, and then I divide by 1/2, that cancels that 1, so that's just going to leave me with u to the 1/2, or the square root of u. I'm not going to worry about the plus c right now. So I'm not going to worry about that right now because this is only half of the integral. And then we said u is x squared minus 4, so this is going to equal the square root of x squared minus 4. So that's this piece of it right here. What about this piece? Well, that, I'm going to bring that down here. Alright, this up a little. So I'm going to bring the 3 out front. Now I have the integral of 1 over x square root of x squared minus 4 dx. Notice that actually fits this pretty perfectly. The only thing we have to consider is that a has to be 2, right? So a equals 2, u is just x, so du is dx. Alright, so let's go ahead and finish this one up then. So I've got this factor of 3 out front, and I've got the integral of 1 over u square root of u squared minus 2 squared du, and we know from here that's going to be 1 over a, where a is 2, so 1/2 arcsecant u, which is x, over 2 plus c. Again, I'm not going to write the plus c right now because I'll put that, when I put this all together, I'll add the plus c. So this is going to be 3 times, we said 1/2 arcsecant of the absolute value of x over 2. Alright, so if we put, that's this is that integran, and this piece right here, not integran, but the antiderivative is this one. So let's put it all together now. Because we took this, we broke it into 2 pieces. This one gave me square root of x squared plus 4, and this one gave me this. So then finally, the answer will be the square root of x squared minus 4. 3 times 1/2 is 3/2 arcsecant of the absolute value of x over 2 plus c. So the trick here was just to break this into 2 integrals. This one was we were able to do with substitution, and this one was an inverse trig integral using the arcsecant. Alright, one last example on this section. Something a little bit different. Look at the integral from 0 to pi over 2 of cosine of x over 1 plus sine squared of x dx. Alright, so this one's a little bit different. What we want to think about is, let's look at here. Right, the only thing that this could possibly fit would be this, because there's no radical in the denominator. So if it's going to fit this, then a would have to equal 1, and u would have to equal sine. Right? So that means that du is the derivative of sine, which is cosine dx, cosine of x dx. So that works out pretty nicely since I have a factor of cosine of x dx right here. The other thing I can do then is change my limits of integration to u, right? So to get the lower limit of integration, I put in 0 for x. Sine of 0 is 0, so my new lower limit in terms of u is 0. And then I put in pi over 2 for x. Sine of pi over 2 is 1, so my upper limit in terms of u is 1, right? This whole thing becomes du over 1 plus u squared. All right, and again, notice that fits this perfectly, right here, with a equal to 1. So that's going to be 1 over a, where a equals 1, so that's just, this first part's going to be 1. We don't usually write 1 when we're multiplying by 1, so I'm just going to write arctan of u over a. So that's going to be, well, actually, I don't have to go back to u. Sorry, I'm just going to rewrite this as arctan of u, because my limits are in terms of u, so I don't need to go back to x. I have arctan of u, well, u over 1 technically, but again, we don't write that. And now we're going to plug in our limits 0 and 1. All right, that's the advantage of changing the limits to be in terms of u, is at the end I don't have to go back to x. I just rewrite this as arctan of u using this. Don't worry about the plus c for a definite integral because that will subtract off. So now what I'm going to do is I just need to evaluate arctan of 1 minus arctan of 0. And this is where reviewing your inverse trig integrals could be helpful. Arctan of 1, another way to ask that is tangent of what angle will give me 1. And that's pi over 4. Likewise, this is asking tangent of what angle would give me 0, and that's 0. So the answer is pi over 4. And again, geometrically that means the area from 0 to pi over 2 underneath this function, between this function and the x-axis, would equal exactly pi over 4. Alright, so these are just a few examples. The basic idea, again, just to quickly recap, is to look for this type of a structure in the integrand. And you may have to, look carefully, as we did in this last example. We saw this 1 plus something squared, and if we let u equal that something, then the du gives me the rest of it. So that's the basic idea, is to become familiar with this structure and look for that in the integrand to recognize the inverse trig integral.